The Lord is risen. Alleluia, alleluia. Truly he is risen. Alleluia, alleluia. All right, guys. So just before I continue yesterday's lecture, is there any questions before I start? Okay. Make sure you're here on time, guys. All right. So I keep on admitting some late. No question? Okay, no question? All right. Okay, Ernest Rutherford, Madav today. Okay, so let's go back to this. So I'm going to share my screen. Not my screen, the iPad. All right, so let me see. Move this on this side. There you go. Okay, still missing 41, 42. Missing about 5 students. Okay, so yesterday we looked at the electrical charge, the amount of electrical charge, which is given by letter Q, or big Q or little q. It's given in Coulomb. So Coulomb is a very, very big number of charges. And then we look also at electrical fields around charges. So electrical field lines, they always start at positive charges and they always end at negative charges. All right. We look also at the potential here, so electrical potential. And for the time being, I told you, like for grade 11, I want you to think about electrical potential in terms of analogy. I mean, next year we're going to define like what it is, like precisely. But for now, it's best like to think of it in terms of analogy. So here I have like 2 plates, a positive and negative plates here. So if there's an electrical field going from the positive plate towards the negative plate. Now, if these plates were infinitely large, infinitely, there wouldn't be like any fields outside. Okay, there would be so no charge would sort of be able to feel an electrical field outside. Now, of course, it's finite, so it's not infinite. So because it's not infinite, there's a little bit of leakage, but there's very little. Okay, so there's very little leakage. Anyway, so the key point here is that if you put a positive charge right in between here and you let it go, there'll be an electrical force acting on this positive charge, and it will move from the positive plate towards the negative plate. And so this is the concept of electrical potential here. Electrical potential, left to itself, a positive charge will always goes from high electrical potential to low electrical potential. In the same way as a mass left to itself will always drop from high height to low height. So I want you to think about electrical potential in terms of electrical potential is to electricity what height is to gravity. Okay. Now the difference in height here, right? Delta H here. Well, you have something like kind of similar here for electricity. You have what is called the difference in electrical potential between one point and another point. And this is called delta V. So V is the symbol for electrical potential. And delta V is called a voltage. So voltage is nothing else but a difference in electrical potential. And as a matter of fact, that's the only thing that we can measure physically, only differences in electrical potential. In the same way as I told you before, you can only measure differences in potential energy. Okay, that's the only thing that is meaningful here. Okay, so as this object, yes, Madav?
So what's the difference between saying electrical potential energy as in UE versus like V, electrical, like in voltage?
Like this UE is electrical potential energy and V is the electrical potential. All right. And so just let me finish here. So as this mass drops down, it loses a certain amount of gravitational potential energy. Now, if you divide this by the mass, you would get a quantity, right? You would get like something. And of course, if we use our formula, this would be equal to G times delta H. Okay, so forget about the G for now. Now, if you do likewise, if you take like the gain or loss in electrical potential energy, a certain amount of charge Q experience, and if you divide by Q, you get what is called the electrical potential difference between those 2 points. All right. So the difference in electrical potential is analogous to difference in height, delta H. Okay. Good. So let's proceed here. Now let's go back to what you learned a little bit in grade 9, or failed to learn, as the case may be. I don't know. You don't have to write this down here. So I'm going to put like in the scrap here. It's just like a review. If you want, you can write it down, but it's just a review. You remember you played with little circuits, right, in grade 9, and there was something like this here. Does anyone remember what this is a symbol of what? Luke, can you mute? Whoops, I don't know who I'm mute. Jason.
Battery.
Yeah, it's a battery, right? Okay. Oh, let me some mute. There we go. Mute. Okay. Yes, it is a battery. That's very correct here. Does anyone remember what the big bar and the small bar mean? Jason? Oh, these guys, like I taught them, right? Jason, Timothy. So you should be like right on top of things. Yeah, Jason.
Yeah. So the big set is a higher potential energy, and the lower set is a smaller one.
That's exactly it. All right. So the higher bar symbolizes the higher potential, electrical potential, and the small is the lower electrical potential. Now, that does not necessarily mean that this is a plate, a metallic. So that doesn't. Let me sort of get rid of this here, chat here. That doesn't mean here that this is positively charged and this is negatively charged. That's not what it means. It may mean this. It just means that this plate here is a higher electrical potential than this one. Now, of course, you need to complete. So this is called a source. We're going to talk about this in a second. Jason, do you still have questions, or your hand is still up? Okay. All right. So this is a source, what we call an EMF source. Okay. Does anyone remember what this is here? Yeah, Max. Max. Problem with your mic?
Sorry, I didn't unmute. Oops. Okay. I don't exactly remember what it's called, but it's like the resistance thing. It has like the
Yeah. Okay, but it's
light bulb.
yeah, it does offer resistance, but it's a specific. So anyone else here? It's specific electrical device. Jason.
A light bulb.
Yeah, a light bulb, right? It's a light bulb. Remember, that's a filament here, right? It's a little filament. What did you learn in grade 9, guys? I mean, not those I've taught you, but the rest. Anyway, so okay. Now, except for Jason, Timothy, Luke, well, Sean, right? Except for these 4 here, I want you to tell me. Okay, there's a chat here. What's that? I want you to tell me too, sir. Sorry, Leo, I apologize. Leo, so 5%. Oh, Ben too, yes, Benjamin, that's correct. Sorry, I apologize. My apologies here. Okay, except for those whom I've taught in grade 9. If I ask you in which direction the current flows, so in which direction does the current flow? Does it flow counterclockwise, or does it flow clockwise? Anyone, except those I've taught. Okay, so Eric, you.
It flows from high potential to low potential.
Okay, so in here it will flow where?
From left, but I mean counterclockwise.
Counterclockwise? Yeah, Dave, do you have something to add? Dave? Dave? You have something to add, Dave? Okay. All right. So what's that? Chat? Chat. No. You mean no? No, what? No, it's not correct. You have a mic, or is your mic working, Dave? I don't have anything to add. Oh, okay. Don't have anything to add. Okay. All right. Okay. So Eric said like it moves from the positive here to the negative here. So like this way. Does anyone so disagree with that? Anyone disagree? No one disagrees? Yeah, David. Okay. All right. Okay. Yeah, that's what I want to say. Okay. So if you ask an electrician in which direction the current flows, this is what it's going to tell you. So the current flows from, as Eric said, from high to low. From high to low. All right. However, when we talk about current, we talk about what is called the conventional current. Whenever you hear current, I mean conventional current. All right. Before I define what conventional current, there's a difference between current and electron. I know current is a flow of charge, right? But there's a difference between electron flow and current. So electron flow, the electron flow is actually in this circuit goes the other way around. It goes from low to high. That's the electron flow here. Okay, and it's saying like so left to itself, remember here, left to itself, a negative charge go from low to high. From low to high. All right, from low to high. All right. So this circuit here, the electrons are actually going the other way around. Okay. But why do we say the current goes opposite the electron flow? Because a long time ago, before they knew what was moving in electricity, they thought that what was moving in electrical circuits, they thought that what was moving were positively charged objects. They thought it was positively charged object. And of course, if you have a positively charged object, it's going to move from high to low. It's only later on they realized that what was moving was the electrons. And they had already assigned the negative sign to the electrons. Now, by that time, they didn't want to sort of change the whole convention. They could have said, okay, so let's make the electron like positive and then the proton negative. They didn't want to do this. Okay, it's akin because like they were like, already for a long time they had assigned a negative sign to the electron. They didn't want to go back. It's akin to like saying like, okay, from now on here, like this hand here is left and this hand is right. Okay, well, if you do this here, then you have to go back to all the instruction manuals to change anything instruction. So that would be like a huge undertaking, right? Okay, so and there's another reason too. Okay. So whenever I say conventional current is the direction that positively charged the particle would take. And if what was moving in electricity were protons, I know they're not moving, but if they were moving, those were allowed to move. They would move from high to low. All right, in the same way as a positive charge moves from high to low left to itself. Okay, so from this point on, whenever I talk about the current, I talk about conventional current. If I want to talk about electron flow, then I will say electron flow. Okay, all right, so okay, so let's before we go to this here, so let's move at let's move right here. No, don't move, guys. Don't move. Okay, I just want to see like it's a little bit like over the place here. Okay. If you want, you can take notes here, but you should already know that here. It's coming. It's coming. It's a little bit slow. Let me stop sharing and I'll share again because it's my poor little laptop has a hard time to keep up. Okay, there's three essential parts in an electrical circuit. First of all, a circuit means something that goes around. So there must be a loop, complete loop. So there's three essential parts to a circuit. So what are they? What are the three essential parts to circuit? Grade 9. No one remembers? Okay, Madav.
Are the source and a ground one of them or two of them?
Ground? Whoops. A ground, you said?
Yeah.
No. No. But the source is fine. So three essential parts to a circuit. Okay, the power source. Yeah, David. Oh, okay. All right. Okay. All right. So let's take. I don't have. Do I have a battery here? Ah, there we go. My battery. Okay. So I have a battery here. 9 volt. Sorry, 1.5 volt battery. So it means that there's a difference in electrical potential across of roughly 1.5. Okay. So one is positive, and the other side is, oh, they don't put the negative side. It just put the positive side. Okay, so there's a positive side here. So this side here is a higher electrical potential than that side. All right. And I can measure the difference in electrical potential across by using a device that's called a voltmeter, which you should have used in grade 9. Depending on your teacher, probably your teacher might have shown you like something with a little needle. But if you're in my class, I did not use this. I asked them like to use a multimeter. A multimeter is a device that combines like 3 types of meter. One is a voltmeter. So there's one here. I don't know if you can see here. It says like DCV. So DC stands for direct current. So the current that goes only in one direction. And V is the volt. So I'm going to set it at 20 so it can record up to 20. And I have 2 terminals right here. This is called the red terminal. This is called the black terminal. And whenever I put this across like 2 points, so I'll do it like right here, right? So here I put the red terminal here, and I put the black terminal right here. Okay, this is so hard to do this without being in class. Anyway, so what this voltmeter does is that it measures the different electrical potential from this one to this one. So basically, it takes the electrical potential of the red terminal minus the electrical potential at the black terminal. So if I do this here, right, and since I have only 2 hands, you're going to see me like disappear. All right, so let's see here. And it's really, really hard. I wish I had like 3 hands. I have to make contact. All right, okay. So now you see a reading here of 1.59 volts. So there's 1.59 volts of electrical potential difference across this battery. Now this battery here is not working too much. So the electrical potential difference is probably higher than what it would be if I were to put it in a circuit, okay? We'll talk about this a little bit later on. Okay, so as you said here, you need a power source, and this is called an EMF source. Okay, so power source. All right. Now, if I had only a battery, and if I want to, I don't have. Okay. With a battery alone, that I'm not going to do much with this, right? I need something else. So what is that something else I need? Yeah, Max.
Oh no, I had a question.
Okay. Day, you'll take it after. Yes, Max.
Okay, so when you have so what does it mean? So when you have like different so you calculated and you said like when the battery doesn't work as well and when it's like being used up,
Yeah,
like the
wait,
difference is greater.
wait. Okay, thank you. Wait, Day.
Can you hear me?
Yeah.
You need a path for like the power to travel.
Okay, so you need the path. So you need, David? Yeah, wires. So conductors. That's correct. So you need conductor. All right. So you need a wire here, conductor. Okay. And what's the last part here? Come on, Madav.
Is it a load?
That's correct. It's called a load. A load, and I'm going to define this in a second here. So these are the three essential parts of a circuit. Now there's a non-essential part, but that's quite useful, is a switch to let you control, right, the flow of electricity. So it's not essential, but it's pretty useful, right? It's pretty useful. Okay, so these are the three essential parts of a circuit. All right, so let's go back to this here. I'm going a bit like fast here because you should have learned this already. Okay, so EMF source. So EMF source, or electromotive force, is a device such as a battery, electric generator, a solar generator, solar cells that transform one type of energy into electrical energy. All right, so anything that converts one type of energy into electrical energy is called an EMF source. Because this is a device that will sort of set, this is a device that will set the electrons into motion. So that's why electromotive force. It generates an electrical field, there's a force, right? It sets those electrons, those charges in motion, all right? So that's why it's called electromotive force. So the potential difference between terminals of the EMF source is called the voltage. And what's the goal of an EMF source? Now, the battery is one type of EMF source. Okay, so battery converts chemical energy into there are chemicals into electrical energy, right? Solar cells, photovoltaic cell, right? Photovoltaic cell converts solar energy into electrical energy. So that's another source. So here it says battery, but it could be like any M source. So the goal of the battery is to provide a difference electrical potential, because if there's no difference electrical potential, there won't be any current moving. I repeat, no difference electrical potential, current will not move. All right. In order for water to flow, you need to have a difference in height. So you have a pipe here, you need to bend the pipes, right? So there must be a difference in height. Or another way of saying this, if you want the water to move in your pipes, there must be a difference in pressure, all right, between 2 points. That also get the water moving, right? So another analogy here is difference in electrical potential is to electricity, what difference in pressure is to water pipe system, right? Okay, so the role of the battery is to provide a difference electrical potential, to maintain the difference, and to move a charge across the difference by expending energy. So this one here, never do this, by the way. This is a short circuit. Don't do that. Make like, you might sort of fry up the battery. Okay, so here you have a 1.5 volt battery. I put a wire. This is called a short circuit. Don't do this. And the goal of this battery here is to take the current at the low electrical potential and to raise it to a higher electrical potential. All right, that's the goal of a source. And of course, it has to expend energy to do that. In the same way, this is equivalent to this little sticky man here. What he does, he takes like bowling ball here, it takes it from down and put them up and then goes back down, right? You drop it, goes back down. So the role here of this person is to take the balls at low electrical potential, at a lower height, and to raise it to a higher height, to raise the gravitational potential energy of this ball, okay? And of course, it does this at the expense of energy, so chemical energy into, right? This is equivalent to someone like pumping, all right? So the role of the pump is to take like the water at low height and to raise it to a higher height. And it does this at the expense of chemical energy in the person, right? Okay, good. So that's an EMF source. Now, a load, now you have to go a little bit like farther down here. Where's the load? Okay. Yes, Max.
Oh, sorry, that I didn't mean to do that.
Okay. So a load is an electrical device that does exactly the opposite. A source, the EMF source, takes some form of energy, converts into electrical energy. A load is exactly the opposite. It takes electrical energy, converts this into some other form. All right, so load is any device that causes or crosses a drop in electrical potential as the current roll through it. We're going to talk about this, but this is the definition here. So any device that converts electrical energy to some other form. So some of the famous one is a resistor. Resistor takes electrical energy, convert this into thermal energy. It should say thermal energy, not heat, but anyway. All right. Does anyone remember what is the symbol for resistor? Anyone? Grade 9? Timothy?
It's like a jagged line. I don't know how to describe it.
Yeah, that's a symbol for a resistor. A light bulb takes electrical energy and converts this into light energy plus heat. There's always heat. There's always thermal energy, except for one special exotic substance material. Whenever you have electricity, it always generates thermal energy. All right. So a light bulb, of course, is this. This is so bad. Okay, so let me use like this. Yeah. Well, yeah. All right. Okay. No, I'm still on. That's what happened. Okay, so you know what it is. Okay, let me do it. There we go. So this is you can put like one loop or two loops. This is the American, by the way, the North American symbols. In Europe, they have a different one. Anyway, you'll learn next year. Or you can learn yourself. A motor. Does anyone know what a motor, what the symbol for motor is? Oh, Natalie.
It's like an M with a circle around it.
Yep. That's correct. All right. So a motor here converts electrical energy into mechanical energy, anything that lift and so on. And of course, there's heat here. Okay. All right. And there's other loads, but these are the most major ones, right? Most major ones. Okay. All right. Now we go back to grade 9, all those 5 or 6 students I taught, like you remember like a diagram like this. Okay. So once again, if you want to understand electricity, which you don't see, you think in terms of analogy. Okay. So this thing here is exactly analogous to that here. The role of a source, an EMF source, to take the current at low electrical potential. So here they put like 0 volt, and to take this current and raise it to higher electrical potential. And in order to do this source has to exert some work, has to perform some work, right? So here, like the work is being done by using up chemical energy that is into the battery, and converting it to electrical energy. This is exactly analogous to this. The role of the water pump is to take the water at low height and to raise it at a higher height. And does it take energy to do this? Of course, right? So the water pump, if someone is doing this mechanically, so eventually it comes from the chemical energy stored in the person, right? And this is converted into gravitational potential energy of the water. So the role of the water pumps to take the water from low to higher height. Now, when you have the water at higher height, what you can do, you can make it flow down, because water mass flows naturally from high height to low height. Well, if you do this, that's fine. It looks like a fall. You can go and see like big falls in Niagara Falls. All right. But you may want to have like this water do some work for you. Well, you put a paddle wheel. So the water here, notice here that the water as it falls loses electrical potential, gravitational potential energy. It turns a little bit into kinetic energy. It converts this kinetic energy to the rotational kinetic energy of the paddle wheel as the water collides with the blades here. Okay, it does work. And then finally, the water loses all this height, this gravitational potential energy, and then goes back to the pump. Well, the paddle wheel here is the same as a load here. So once the water is raised to a higher height, the goal of the source is to raise this to a higher electrical potential. Once the higher electrical potential, current left to itself will fall from high to low electrical potential. So you can sort of make it like go this way, a simple with a wire. Of course, it's not going to do much for you. You might sort of fry the battery in doing this. So what you do is you put a load. And then the load, what happens here is that this current here, as it loses electrical potential energy, it converts this into some other form. This is a motor, so it converts this loss of electrical potential energy into mechanical energy. Okay, and then once the current is at the lowest electrical potential, it comes back. And then the whole cycle continues. Okay, all right. So what does it say here? That's for the fan. Yeah. So in any loads, you don't have a 100% efficiency, right? So what you want to do for you electric motor, you want the electric motor to give you mechanical work, right? So something turning. Unfortunately here, you're always gonna have non-desired energy, and usually it's thermal energy, right? You don't want the motor to create thermal energy. You want it to create rotational energy, but you will have thermal energy. So this is called the waste here, right? So it's never 100% efficient. No electrical devices are 100% efficient. Okay, so symbolically, this is equivalent to this. Forget about this here. You don't have to put like the big bar here. By the way, here, there's a bit of a difference here. A battery is called an electrochemical cell. So it's a source that converts chemical into electrical energy. When you put electrical cell, when you combine them in series, you can add up the voltage. So a battery is a collection of electrochemical cell that plays in series. Anyway, we'll talk about this later. Okay, so you good with this? All right. Okay, so let's go back here. Okay, so Max. Max, are you there?
Yes.
Okay, so keep your mic up here. Okay, go back to this here. Okay. All right. So let's say here, actually, you know what? Let's go to this diagram here. Yeah, let's go to this diagram. My beautiful diagram. I'm so gifted for drawing. Are you there, Max?
Wait, oh, yeah. I thought all the bowling balls were people's heads.
No, these are bowling balls. Come on, I'm not gonna roll like people's heads.
I'm sorry.
Yes, I'm not that gruesome. Okay, everyone there? Okay. Okay, so the goal here of this person here is to raise the bowling balls, not the heads, bowling balls from low height to high height, right,
Mm-hmm.
Max?
Yes.
Okay, and then see here, you lift this up like 2 meters, okay, by 2 meters, right?
Okay. Yeah.
Okay. Now, let's pretend here that you're this person here. You lift those bowling balls up. Now, if there's only one or a few bowling balls coming every 10 seconds, it'll be like fairly easy for you to do that, right?
Mm-hmm.
Right? Yes or no?
Yes.
Okay. What about if you have like 3 bowling balls coming every second? What will happen to you?
It'll so they'll be coming at a fast rate at which I can lift them up, so it'll start like flowing down. and, like,
Okay,
clog
but
them.
what will happen to you? Like, let's say you have like
I'll
five
get very tired.
coming every second, and your goal is to move them up. So what
Yeah.
is going to happen?
I'll get really exhausted.
You'll get very exhausted. In other words, you won't be able to raise it as high as you want, right?
Yeah.
Right? Well, this is exactly the same thing for this. You can mute yourself here. All right? It's
Okay.
exactly here. When there's no load, on this source, it's pretty easy, like to maintain a voltage of 1.56. But once I make it work, there's current flowing through it. It won't be able to maintain a voltage of 1.59. It'll drop perhaps to 1.4, perhaps even 1.3 volt. Depends how strong it is. So that's why when you have a load on the circuit, the source will not maintain the same electropotential difference as if there's no load. Okay, so that's a reason for it. And that's the reason why here this is called a short circuit. What happens here is there's an enormous amount of current, and the battery has to raise this up. Then it cannot do it. It's too much, right? So it'll deplete all its chemical energy, and it will catch fire and so on. So that's why it's called a short circuit. Okay, so let's go back to this here. All right. And then okay. All right, so let's pretend here. I didn't mention this before, but let's pretend that you have a certain mass. A little certain mass here. And sorry. That's the Earth here. All right, so what you want to do here is you want to lift this mass. So you want to lift this mass a certain height. Now let me do this here. I like when it's neat, as you may have guessed. There you go. That's better. Okay. So let's say here you want to sort of raise this this mass. Now, if I ask you, what's the minimal force that you need to apply in order to lift this up? What's the minimum force, guys? Yeah, someone else but Max. What's the minimum force you require, guys? Someone else? Someone else? No, not Max. Someone else. Okay, let's say Justin. Justin Gu. There you go. Justin, unmute yourself. Justin, so what's...
Can you hear me?
Yes, I can hear you.
Okay, the force would be the weight, mg.
That's correct. That's correct. Okay, so the minimal force here, so let's look at that here. So there's the gravitational, the weight, right? And so the minimal force, all right, will have to be equal to the weight. You know, absolutely correct here, okay? And so if the applied force is equal to weight, then the object will move at constant velocity. All right. So minimum force required to lift is Fa is equal to the weight, which is equal to mg, right? Now, if we look at the work done by the applied force, so the work done by the applied force is the work done, I'll put it here, because I can see here I'm gonna need like more space. Ooh, look at that. Oh, beautiful. Yeah, oh, beautiful. There you go. All right, so the work done by the applied force is equal to this times delta D times cos of the angle, which of course will be like 0 here, right? By the way, here, like the mass will go up at constant speed, constant velocity. Okay. Now, cos of 0, of course, is 1. Delta D is nothing else but delta H. This Fa is equal to mg. And what you have here, you have this, right? Well, what is this here? Well, this is nothing else but the change in gravitational potential energy, right? As you go from this height to that height. All right. So the work done by you, the minimal work done by you, right, will be equal to the change in gravitational potential energy of mass, m. So this is another definition of potential energy. Another definition of potential energy, differences in potential energy, is as follows. Differences in potential energy of a system is equal as to the work done by an external agent in moving a system from initial configuration to final configuration at constant velocity. Okay, so that's another definition of potential energy. Okay, so if we go through this here, for gravity here, the work done by external force and external agent in moving a mass at constant speed and gravitational field is equal to the change in gravitational potential energy, right? Now, if I take this, so if I take this and divide by m, so this is equal to work here. If I divide by m here, right? If I divide this by m, delta UG divided by m, I get G delta H. So W divided by the work done by me over m corresponds to G times the change in height, okay? Well, you have something exactly like similar here. So this is not a quantity that we use, right? By the way, here, like for instance here, if it takes, so what it tells you here, it tells you that, let me see here, like 2 Newton or 1 gram. Okay, this tells you how much work you need to be done, how much work you need to do against gravity per unit mass. That's what this is here, all right? So the amount of joule per kilogram, okay, the amount of joule per kilogram. So if you lift this by 1 meter here, and G is equal to 10, right? So this corresponds to 10 joule per kilogram. So what it means here, it means this is the amount of work that you need to do to lift per kilogram, to lift a certain amount by 1 meter, okay? So 10 joule per kilogram. So if you have 2 kilograms, then you would require 20 joule of work. If you have 3 kilograms, to lift this over 1 meter, you would require 30 kilograms, all right? Okay, so electricity, you have exactly the same thing here. The work done by an external force in moving a charge, right? Moving a charge at constant speeds in electrical field is equal to the change in electrical potential energy. The same way as this, the work done by this applied force to move this mass from here to here is equal to the change in gravitational potential energy. Same thing happens here for electricity. Now, if I take this, if I take delta U here, the change in electrical potential energy experienced by the charge, and divide by the charge, or another way of saying this, the work done by me divided by how much charge, what I'm gonna get here, I'm gonna get something that is called the electrical potential difference, all right? So electrical potential difference is also defined as the work done in bringing an amount of charge Q from one location to another location at constant velocity per unit charge, okay? So that's what like a difference electrical potential difference is, right? So the amount of work needed by an external agent in bringing a certain amount of charge Q from one location with one specific electrical potential to another location with another different electrical potential, okay? So, so delta V, once again, is analogous to delta H, right? Like differences in electrical potentials to electricity, what difference in height is to gravity, what difference in pressure is to water pipe system. Okay, so we say that there's an electrical potential difference of 1 volt between 2 points. So if you have like 2 points here, we say that there's an electrical potential difference of 1 volt. All right, so there's an electrical potential difference between 1 volt. If let's say here, like there's 1 volt of difference here. So I have my voltmeter here, of course it's off. And let's say here it says that there's 1 volt. So there's an electrical potential difference of 1 volt between 2 points if it requires 1 joule of work in moving 1 coulomb of charge from one point to another point, okay? So for instance, this one here, remember? This is 1.5 volts here, right? This is positive, this is negative. What it tells you here, the electrical potential difference tells you here to move this battery here, this source, to move 1 coulomb of charge from here to here, it would require 1.5 joule of work. Of course, it requires like probably a little bit more because it's not like 1.5, but anyway, it would require, if it were perfectly, if there was no loss and so on, it would require 1.5 joule. The battery has to expend 1.5 joule of energy, chemical energy, in order to raise 1 coulomb of charge from low to high, okay? So that's what it means. So you can see here, like the volt is nothing else but joule per coulombs, okay? Good. All right, so, okay, so if I use this, if I bring like Q on the other side, if I bring Q on the other side, what I get is this. The work is equal to Q times delta V. So the work that needs to be done in order to move like a certain amount of charge across a electrical potential difference of delta V is this. The same way as the work required by me to move a certain amount of mass from a certain height to another height is equal to M times G delta H. Now remember Q, we can express this in terms of current, remember? Right? All right, so if you express Q in terms of I and delta T, this is what you get. So the amount of work required by a source are to transport a certain amount of current over a certain amount of time over a certain amount of electrical potential difference is equal to that. Okay. Now remember, power is the rate at which work is done, so W over delta T. So if you use this, put this equation here, delta T disappear, and you get this. So that's a very interesting equation here. So the power of an electrical source, or electrical load too, is equal to current times the voltage across it. The current that goes through it times the voltage across it. So if you use like your, and you remember watt is, power is given in watt. So for electrical devices, 1 watt is equal to 1 amp times 1 volt. Okay. All right. So let's finish this here. Let's do some example here. Okay. So example 3. Boop. Example 3. All right. So let's do example 3. Okay. Okay. So found the amount of electrical energy on the amount of electrical energy used up by a light bulb Okay, so find the amount of electrical energy used by a light bulb. What was the previous light bulb? It's the same light bulb as before, all right? So, oops, sorry, guys. So find the amount of electrical energy used up by the previous light bulb. In, let's see, 5 minutes, if it operates across a voltage of 120 volts. You're gonna see those problems are really easy. Even if you don't understand what's going on here, if you're good in math, okay, I know the givens, I know the required, whoop, find it, okay? Of course, you need to, physics is more than that, right? Right, much more. I'll be back. I'm just looking for my extension. All right, I'm back. All right, so you have electrical outlets. Electrical outlets here, you have two holes here, 2 slits. And what it does is that it provides a different electrical potential. So one slot is at ground voltage, so roughly like 0. And the other one is at a higher or lower. Anyway, let's see, we'll keep it like higher for now, all right? And it's roughly at 120 volts. So this one here is 120 volts. This is 0 volts. Now, when you connect something, and connect, so this is your light, at the end of this is your light bulb here, right? When you connect this, is you make sure here that this side here is connected to the high electrical potential and this side is connected to lower electrical potential. So what happens here is that current goes from high to low. So current goes in from high, goes through your light bulbs and comes back to the low, all right? And goes back to the ground, forming a loop, okay? So most devices at home operates across 120 volts. Yes, Max.
Wait, is that why every plug has 2 sticks and not 1?
Yeah, there must be, because there must be a difference in electrical potential. Yes, that's correct.
Okay. I never knew
Right?
that. That's
Otherwise, it's
interesting.
not going to move. Right?
Okay.
Okay, good. All right, so it's pretty easy here. So what are we looking for? You're looking for, well, what do we have? Well, we have, how much current was this light bulb taking? I don't remember. David? 2 amps. All right. We have also the voltage difference, which is 120 volts. We have also time, but you have to change this into, of course, you have to change this into seconds, right? Yeah, sorry. I know that you want to, so 60 seconds divided by minute. So it'll give us like 300 seconds. What are you looking for? So whenever they say electrical energy being used up, electrical being generated for a source, they mean really the work, all right? So they are interchangeable, okay? They are interchangeable here in this case, okay? They're interchangeable. I repeat, they are interchangeable, right? If we go back to this here, all right? So the work done by an external source is equal to the change in gravitational energy. Sorry, the work done by me in changing the mass from one initial height to a final height is equal to change in gravitational energy, right? Okay, so, well, you just use the equation here. It's gonna be this, almost done. So it's I times delta V, well, times delta T, doesn't matter where, times delta V. So it's 2 amps, 2 times 300 seconds times 120 volts. So it'll be 6, so it'll be like 72,000. Am I correct, guys? Is it 72,000? Yeah, okay. All right, so what do you think this unit is? Amp times second times, well, let's put this here. So this is like 72,000. Amp times seconds is Coulomb times volt, and a Coulomb times volt is equal to a, yeah, Dave?
Is it a joule?
Yeah, are you asking me?
A joule?
Yeah, it's a joule, right? So this is how much electrical energy is being used up by the light bulb. So the light bulb will take this electrical potential energy, it will lose this electrical potential energy, and will convert this into solar light energy and thermal energy. All right. So this is that much. Okay. Did I put an A? Yeah, I put an A. You good? Okay, so find the power rating of this light bulb. Okay, so you can use like the definition of power, which is energy, work here, right, divided by the time. But what we're going to do here, we're going to use the electrical formula, right? So we're going to use this. Now, we always talk about difference in electrical potential. That's what is meaningful. So since what's meaningful is only changes electrical potential, this is called a voltage here. What we do very often is we drop like the delta, but you have to understand here that it's always a difference electrical potential. Right? Okay, so we put this, it's 2 amps and then 120 volts. Give you like 200, boy, this is a, so amp times volts, and amps times volt will give you, of course, watt. So this is the power rating of this humongous, not highly efficient, like very powerful electrical light bulbs. So it's going to blind you. It's a floodlight of some sort. Okay, so what does that mean here? It means that every second, remember here, this is 240 joule per second, right? Every second, this light bulb consumes 240 joule of electrical energy. All right, that's what it means. Or every second, this light bulb generates 240 joule of light energy and thermal energy combined. All right, combined. All right. Right. So once again, a source, an electrical device that takes some type of energy and converts this into electrical energy. A load is exactly the opposite. Very often, a load can work as a source. Okay, the other way around. Well, I'll talk about this later. Okay. Okay, questions? You good? Okay, so you got your homework. Okay, thank you, Max. So you got like quite a few homework here, quite a few, questions. They're not like really difficult. Once again, it's just to find the proper equation, isolate for it. Okay, and so work on this, and then I'll see you tomorrow at 2:30, right? On Wednesdays, it's always at 2:30 because I cannot teach you at 11 o'clock. I have a meeting, all right? Questions, Max?
Are you gonna leave us like another like sheet to do before the class starts?
A sheet?
Or like
You mean to download?
no, because last time when you had the meeting, like so you had us like in the morning of that day, like do some work and then we'd ask you.
No.
Okay.
No. All right. Okay, guys. So I'll see you tomorrow, guys. God bless, and don't forget to do those homework here. Okay. Bye.